So our last speaker for this morning session is Dr. Wanheng. So Dr. Lu is currently a research fellow at the Department of Electrical and Computer Engineering, National University of Singapore. Her major research covers employing multiple scanning probe microscopy or SPM-based techniques. Please welcome Dr. Lu.
Good morning, everyone. Firstly, I would thank Mr. Pu and the Park System for inviting me to this symposium to share my knowledge about the scanning probe microscopy techniques. Today, I named my presentation as the dance of the light and photocatalyst. I borrowed this name from the book, A Song of Ice and Fire. Hopefully, my presentation today could leave you a good image similar to the impression of this book to its readers. Before my presentation, I'd like to give you a brief introduction about myself. My name is Wanheng. You can call me Wanheng, just like my friends do. Currently, I'm a research fellow from NUS under the Department of the Electrical and Computer Engineering. I'm in whole research group, also known as the Sustainable Smart Solar System S4 Lab. If you want to contact me after this presentation, you can reach me at these email addresses. Okay, in my research experience, I have used the following SPM techniques to study a range of materials properties. For example, we use the AFM to study the topography, use the conductive AFM to study the electrical property of materials, and also use the KPFM to study the material surface potential, surface charge, and also the work function. The right side shows some images we have obtained previously. This image we have, for example, we have the surface potential of the 3D printed 316 stainless steel. We're also using the AFM to detect the thickness of the 2D materials and using the magnetic force microscopy to determine the phase of these duplex stainless steel materials. And this is the application of PFM to detect the phase and also the ferroelectric switching rope. And this is the application of conductive AFM. Oh, sorry. Not finished. Okay. To some extent, I'm a proficient SPM user. So today I'm here to share some of my knowledge and experiences for conducting SPM testing, especially the KPFM testing for inorganic materials. This is my presentation today. I separate my presentation into 3 parts. Firstly, I will go through some basic principle of KPFM and photocatalytic hydrogen generation. And after that, I will show you the interaction between the light and photocatalyst revealed by using KPFM. This interaction include photothermal and the photochemical interactions. Then I will summarize the content. Okay, so let's start with the KPFM. KPFM can be used to measure materials work function and surface potential by detecting the local contact potential difference, or CPD, between the tip and the sample. The CPD is created due to the work function difference between the sample and tip. When a KPFM tip and sample is electrically connected, the electrons will move between them. For example, here, the electrons will move from the sample with a lower work function to the tip, which has a higher work function. As the electron move, both tip and sample will be charged to create a potential difference between them. So this is the contact potential difference. If a DC voltage, which has the same amplitude but opposite direction to CPD, is additionally applied, so the potential difference between the tip and sample will become zero. This equation shows the relationship between the work function and the CPD. If we can get a method to know the CPD or the DC, we can know information about the material's work function. Okay, now let's have a look at the KPFM system to see how it works to measure this CPD. Essentially, KPFM is one of SPM techniques, which is based on detecting the electrostatic force between the tip and sample. This electrostatic force can be written as the function of potential difference between the tip and the sample. Specifically, during the KPFM testing, both AC and DC voltages are applied to the KPFM tip. The AC voltage will generate oscillating electrostatic force between the tip and the sample, and the application of the DC voltage will zero this oscillating electrostatic force. So by recording the DC applied to zero this oscillation, we can know the work function of materials. This is one example. From this, by conducting the KPFM study, we can see that the work function of the nickel oxide thin films has changed by electrical pooling. And also because the electrostatic force is directly related to the potential difference between the tip and the sample. So KPFM can be used to study the surface potential and surface charge. And this is one example for this application. Before the KPFM scanning, we use the area inside this dash box has been wrapped by a contact AFM tape to generate tribal electricity in this area. This generated tribal electricity has been clearly demonstrated by this shining yellow box. Okay, so for most SPM users, for example, the simplicity is the beauty. So here is my liquid tape for a quick KPFM data analysis. That is the increase of the DC or CPD means the decrease of the work function and also the surface potential increase or positive charge generation. But before you using these tips, make sure to check your system if your system is the tip based or the sample based. Okay, now we will answer why we choose to study the hydrogen generation. We choose hydrogen because its potential to generate power and use as a fertilizer and also for combustion. And hydrogen is considered as clean and green energy, which leaves no carbon footprint. And hydrogen is also easily stored and transported. As a refresher here, to obtain hydrogen, we can use the water electrolysis method. But here, I want bring your attention to another method, which is the photocatalytic hydrogen generation. In this photocatalytic hydrogen generation, a photocatalyst absorbs the light energy to create the electron and hole pair, and then the electron are transferred to active sites to generate hydrogen. This method does not require electricity, which can directly convert the energy of the light, for example, the sunlight, into hydrogen to this chemical energy. And from this figure, we can see that the photocatalyst is the key point because it determines the light absorption, charge generation, and also the charge separation, spatial separation required for hydrogen generation. Okay, now I will let's take the KPFM as glass. We will see the dense show of light of light and the photocatalyst. In this show, we will see a KPFM case study on a hybrid photocatalyst, which is developed by my colleagues at NUS. And this related work has been published at Advanced Functional Materials. If you need more information, you can refer to this paper. Okay, this hybrid photocatalyst has a full spectral light absorption and exploitation. For example, the visible near-infrared light can be confined by silver. Okay, well, where is my spot? Here. Can be confined by the silver nanoparticles to oscillate the conduction electrons of silver to make the electron of silver nanoparticles oscillate coherently with this with the light. This is the so-called localized surface plasmo resonance or LSPI effect. Due to this LSPI effect, the silver nanoparticle can absorb the visible light and provide a localized heating to accelerate the hydrogen generation. And the UV light can be absorbed by the titanium oxide to generate the electrons for hydrogen generation reactions. Studies at macro scale have demonstrated this photothermal and photochemical interaction have enhanced the hydrogen generation. But why and how it happens at a narrow scale. Do we have any evidence to support this hypothesis and to show the localized heating or the charge generation, charge distribution? Do we really have any evidence to this? Okay, as discussed, we can see that both the photothermal and photochemical interaction are related to the charge generation or transfer. As we mentioned before, KPFM can be used to study the surface potential, surface charge. So it can be used to study this interaction between the light and the photocatalyst. Luckily, the SPM techniques is a really flexible platform where we can easily engage multiple and diverse external fields to study materials response to these fields. So specifically for this study of the interaction between light and photocatalyst, what we need is simply adding a light source with required wavelengths or power. That's okay. It's very simple. SPM techniques is a very flexible platform. Okay, so first to study the photothermal interaction, we decouple the hybrid photocatalyst. We using these two types of sample as the research subjects. One is the silver silicon oxide. Another one is the pure silicon oxide. From this result, these are images, CPD images of these two samples under different light condition. From this, we can see that a significant CPD increase is found on silver silicon oxide at visible light, but similar CPD change with the light illumination condition do not appear on pure silicon oxide. This result indicate a strong interaction between the visible light and the silver nanoparticles. To understand this strong interaction, we use the tips for quick KPFM data analysis I mentioned before. That is, the CPD increase means the decrease of the work function. We just remember here, and then we go to see the particle. Okay, here the particle itself. The visible light can be absorbed by silver nanoparticle to make electron oscillation or hot electron generation, which will cause the Fermi level to shift upwards and to decrease the work function. And now the work function decrease means the CPD increase, which agree with our KPFM result. So here, via this study, actually we can provide a narrow scale evidence to support these photothermal interactions between the visible light and the silver nanoparticles. Okay, later we try to study the photochemical interaction between the in these hybrid materials. In this talk, we prepare two samples. One is with gold addition, another one with no gold. So these are the CPD images of these two samples and different light condition, the CPD increase is found on both samples on the UV light, suggesting that the photochemical interaction leads higher light energy, that is the UV light. And CPD increase of the STA sample is larger than that of ST sample, indicating that the gold nanoparticles are critical for charge transfer and spatial separation. To understand this, we're also using the tapes. The increase of the CBD means the surface potential or positive charge generation on the surface. Okay, we come to the particle itself. The UV light has sufficient energy to photo-excite the TiO2 to generate electrons and holes. Due to the work function alignment between the silicon oxide, titanium oxide, and gold, the electrons tend to move to gold and then to be ground by the PT substrate, leaving positive holes on the surface of TiO2 to increase the surface potential. Without the gold, the electrons cannot get quickly transformed, and then the electrons may recombine with holes. That's why the surface potential of the ST sample without gold is lower than that STA sample. Okay, here this study will also shows a narrow scale image of the photochemical interaction between the UV light and the hybrid photocatalytic. Okay, now it's time for my summarize. Okay, in this talk, we discussed the combination of KPFM and a tunable light source to study the photothermal and photochemical interaction between the light and the hydrogen hybrid photocatalyst. From this work, we can see that the KPFM and the SPM can work as a useful, flexible platform to include multiple and diverse external fields in our measurement, which enables in situ and in operandum studies on materials response to these multiple external stimuli. Okay, at the end of this work, I want to thank contributors to this work, especially my boss, Prof. Ho Gen Wei from NUS. And also, I want to express my special thanks to Prof. Deng Kaiyang from NUS for his guidance and support for SPM testings. And also also thank group members of whole research group and Deng Kaiyang's research groups. These guys makes the day in the lab to be interested. Okay, if you need more information or if you have any idea to share with us, please contact us. We are whole research group as for lab. Okay, now it's my time for question. Which four? This is four. Which 4S? Do you remember? Okay. So can we just go back to the previous. Sorry. Okay. Okay. No one remember. Okay. That is the sustainable smart solar systems. Okay. Take out your handphone, scan this QR code. Okay. So now it's your turn for question.
Hello. So thank you very much, Dr. Lu. So any questions from the floor for Dr. Lu? For our online participants? Thanks for the nice talk and wonderful talk. Sorry.
When you apply for catalysis, I'm just wondering, the KPFM can be applied to other researches that is closely related to localized surface plasma resonance. Any types of research, like source or other
Source.
Source means the surface enhanced Raman spectroscopy that usually, localized surface plasma resonance phenomena.
Sorry, I don't know that that techniques.
What I mean,
So
yeah, KPFM you use for the photocatalyst mechanism.
yeah, for sure.
So that technique can be also applied to other researches. The like surface plasma resonance.
Yes, can
Can be.
Can be used. Yeah. Actually, SPM, the whole platform can be combined with other techniques. For example, the IR shared by this prof this morning. Yeah. And also we can combine with other, for example, X-ray source or other source to do the combination and to do the material, the study.
Good question.
Okay.
What is the resolution limit of the
KPFM. Actually, it depends on the tape itself. Or the AFM resolution depends on the diameter of the tape, and also for the KPFM itself, because we will apply electric field on the tape. So actually this resolution will be larger than the tape itself. And the tape itself, because we were using the conductive tape, which has a coating on the silicon, so the diameter will be larger. And at the same time, to increase the resolution of the KPFM itself, actually we can control the environment of our testing. We can put the sample in a moisture-free environment. That method will enhance the high resolution, significantly enhance that resolution, because the moisture in the air will form molecules on the tape and the sample, the junction. This junction will blur our scanning, which will decrease the resolution.
What I understand in your structure of this KFM, your description of the KFM, okay, you're measuring the difference of the walk function, I understand.
Yeah.
But like, what is different from the STM image scanning tunneling thing is this just like a difference of the number of the electric field, like the amount of the electric field that you apply? If you can apply like a more bias into your KFM, then is it more like a similar like STM?
Actually, these two techniques are different.
I know, but like,
yeah.
What if like you apply the more bias? What if you apply the more electric field? Then it is possible to like induce some tunneling currents, isn't it? then it should be similar as STM, and the STM resolution is like atomic scale.
Actually, for KPFM, that resolution it's very hard to hit. Hit the resolution as the STM. Whereas we know STM, if we want to get a high resolution, we better to do the testing on a ultra vacuum condition, right? So, but for most cases, we just do the KPFM in the ambient environment, and also we actually the distance between the tip and sample for KPFM is larger than the STM, right? So this is also the reason that the KPFM resolution is not so good as the STM, but for user convenient, the KPFM is very convenient. It's easily accessible. Yeah.
Yeah, I agree. Yeah, thank you very much.
Thank you.
Okay, we have a number of questions online also, Dr. Lu. So first is, have you conducted charge separation and charge transfer efficiency of your photocatalysts? I will repeat. Have you conducted charge separation and charge transfer efficiency of your photocatalyst?
Yes, we have do this study, but not using the KPFM techniques. We just use other macro scale studies, but that one is not my expertise. So that part of work are done by my colleagues. If you need this information, you can contact us, and I will ask my colleagues to help me answer this question.
Okay, we understand that, Dr. Lu. Another question is, what in your CPD plots of silver NP samples in light and dark, the change in yeah, it's quite long, so you can read it with me. Yeah, CPD plots, yeah, samples in light and dark, the change is around 10 MV. Which mode did you see, amplitude modulation or frequency modulation? Also, what was the resolution to the CPD?
Okay, actually in the testing, we use the amplitude modulation. This is commonly used in normal condition. Okay, and the CPD resolution, we do this testing in a controlled environment without the moisture. So the resolution, CPD resolution can be around several millivolt. Yeah.
Okay. So for our next question, what is the difference between conductive and piezoelectric response? Piezoelectric response. So what is the difference between conductive and piezoelectric response?
Okay, actually these are two types of the. Okay, can we just go back to my slides and I show you the conductive AFM and the PFM. The page, I think, should be page 3. The page number. Number 2. You see the cycle. I summarized my previous research that page. It's one circle.
Okay, for a moment.
Okay, maybe I can explain. For conductive AFM, if we just we put it simply, the conductive AFM is we apply. Not this one. Oh, okay, here this one. For the conductive AFM, we just think the tip as a as a line to connect the voltage and the tip. Okay, so here we will form a circuit, electric circuit here. We apply voltage and then we measure the current to see the the electrical property of materials. For PFM, piezoelectrical, actually it's piezo response force microscopy. We use this one. Both modes are contact modes, and for the PFM one, we apply AC files to oscillate the tape and the sample together, and then we can get the response, the piezo response. There's no electrical circuit for in this PFM. It's too different.
Okay, thank you very much, Dr. Lu. So if there's no questions from the floor, I think that's all. So thank you very much, Dr. Lu.
Okay, thank you.